Hello everyone, I am Kulpreet Kaur from BSc Chemistry Honors final year student. Today I am going to prepare an audio recording for visually impaired student on the topic of solvent extraction. First of all, general discussion. Liquid-liquid extraction is a technique in which a solution is brought into a contact with a second solvent, essentially immiscible with the first, in order to bring about a transfer of one or more solutes into the second solvent. The separation that can be performed are simple, clean, rapid and convenient. In many cases, separation may be affected by shaking into a separatory funnel for a few minutes. The technique is equally applicable to trace level and large amount of materials. In the case of inorganic solutes, we are concerned largely with the samples in aqueous solution, so that it is necessary to produce substances such as neutral, metal chelates and ion association complexes, which are capable of extraction into organic solvents. For organic solutes, however, the extraction system may sometimes involve two immiscible organic solvents rather than the aqueous organic type of extraction. The technique of liquid-liquid extraction has of course been widely used to separate the component of organic systems. In particular, solvents extractions may be employed to effect a cleanup and to achieve concentration of the solutes of interest prior to analyze. This is illustrated by the cleanup of steps which have been used for the analysis of organochlorine pesticides at the 0.1 μg level in animal fats and dairy products. In one such procedure, the solution of animal fat is hexane is extracted with the three successive portions of dimethyl formamide saturated with hexane. The combined DMF extracts are washed with the hexane saturated with DMF to remove any remaining traces of fat. After separation of the hexane, it is equilibrated with further DMF to reduce loss of pesticide residue. The pesticide compounds are finally partitioned back into a clean hexane after adding water to the combined DMF extracts. The hexane layer is used for the water to combine DMF extract used for the quantitative analysis of the extracted pesticide residues using gas chromatography with an electron capture detector. It is of interest to note that the extraction procedure involves two organic phases and that miscibility is minimized by saturating each solvent with the other. Extraction procedure for organic species, however, do not in general possess the same degree of selectivity as may be achieved for metal containing system. The chief analytical application of solvent extraction is for the determination of metals as minor and trace constituents in various inorganic and organic materials. Although solvent extraction has been used predominantly for the isolation and pre-concentration of a single chemical species prior to its determination, it may also be applied to the extraction of groups of metals or classes of organic compounds prior to their determination by techniques such as atomic absorption or chromatography. To understand the fundamental principle of extraction, the various terms used for expressing the effectiveness of a separation must first be considered. For a solute A distributed between two immiscible phases A and B, the Nernst distribution law states that provided its molecular state is the same in both liquids and the temperature is constant, concentration of the solute in solvent A upon concentration of the solute in solvent B is equal to A upon me AB is equal to KD, where KD is a constant known as distribution coefficient. The law as stated is not thermodynamically rigorous. The activities of the various species and the for reason would be expected to apply only in very dilute solutions where the ratio of the activities approaches but is a useful approximation. The law in its simple form does not apply when the distributing species undergoes dissociation or association in either phase. In the practical applications of solvent extraction, we are interested primarily in the fraction of the total solute in one or other phase, quite regardless of its mode of dissociation, association, or interaction with other dissolved species, it is convenient to introduce the term distribution ratio D. D is equal to Ca upon Cab, where the symbol Ca denotes the concentration of A in all its forms as determined analytically. A problem often encountered in practice is to determine what is the most efficient method for removing a substance quantitatively from solution. It can be shown that if a volume ml of, say, an aqueous solution containing x naught gram of a solute be extracted n times with volume ml portions of a given solvent, then the weight of solute xn remaining in the water layer is given by expression xn is equal to x naught dv upon my dv plus may v whole the power n, where D is the distribution ratio between water and the given solvent. It follows therefore the best method of extraction with a given volume of extracting liquid is to employ the liquid in several portions. Rather than to utilize the whole quantity in a single extraction, this may be illustrated by the following example. Suppose that 50 ml of water containing 0.1 gram of iodine are shaken with 25 ml of carbon tetrachloride. The distribution coefficient of iodine between water and the carbon tetrachloride at ordinary laboratory temperature is 1 by 85, that is at equilibrium the iodine concentration in the aqueous layer, that is 1 by 85th of that in the carbon tetrachloride layer. The weight of iodine remaining in the aqueous layer after one extraction with 25 ml and also after 3 extractions with 8.33 ml of the solvent can be calculated by application of the above formula. In the first case, if x1 gram of the iodine remains in the 50 ml of water, if concentration is x1 upon 50 gram ml, the concentration in the carbon tetrachloride layer will be 0.1 minus x1 upon 25 gram milliliter. The concentration in the aqueous layer after 3 extraction with 8.33 ml of carbon tetrachloride is given by x3 is equal to 0.1 1 by 85 into 50 upon 85 plus 8.33 whole the power 3 is equal to 0.0000287 gram. The extraction may therefore be regarded as visually complete if we confine our attention to the distribution of a solute A between water and an organic solvent. We may write the percentage extraction E% as E% is equal to 100 A naught V naught upon me A naught V naught plus me AW VW is equal to 100 D upon D plus VW upon me V naught, where V naught and W naught represent the volumes of the organic and the aqueous phases respectively. Thus, the percentage of extraction varies with the volume ratio of the two phases and the distribution coefficient. If the solution contains two solutes A and B, it often happens that under the condition favoring the complete extraction of A and some B is extracted as well. The effectiveness of separation increases with the magnitude of the separation coefficient or factor B, which is related to the individual distribution ratios as follow. Beta is equal to A naught upon B naught upon AW upon BW is equal to A naught upon AW, B naught upon BW is equal to dA upon dB. If dA is equal to 10 and dB is equal to 0.1, single extraction will recover 90.9% of A and 9.1% of B. A second extraction of the same aqueous phase will bring the total amount of A extracted up to 99.2%, but increases that of B to 17.4%. More complete extraction of A thus involves an increased contamination by B. Clearly, when one of the distribution ratios is relatively large and the other very small, almost complete separation can be quickly and easily achieved. If the separation factor is large but the smaller distribution ratio is to sufficient magnitude that extraction of both components occurs, it is necessary to resort to special techniques to suppress the construction of the unwanted component. Factors favoring solvent extraction. It is well known that hydrated inorganic salt tend to be more soluble in water than in the organic solvents such as benzene, chloroform, etc., whereas organic substances tend to be more soluble in organic solvents than in the water unless they incorporate to a sufficient number of hydroxyl, sulfonic, or other hydrophilic groupings. In solvent extraction analysis of metals, we are concerned with methods by which the water solubility of inorganic cations may be masked by interaction with the appropriate reagents. This will in fact remove some or all of the water molecules associated with the metal ion to which the water solubility is due. Ionic compounds would not be expected to extract into organic solvents from aqueous solution because of the large loss in electrostatic solvation energy, which would occur. The most obvious way to make an aqueous ionic species extractable is to neutralize its charge. This can be done by formation of a neutral metal chelate complex or by ion association. The larger and more hydrophobic the result molecular species, the better will be its extraction in chelation complexes. The extraction metal ion coordinates with a polyfunctional organic base to form a stable ring compound, example copper 2 acetyl acetonate or iron copper ferrate. The factors which influence the stability of metal ion complexes, which have been discussed in section 2.23, but it is appropriate to emphasize here the significance of the chelate effect and to list the features of the ligand which affect chelate formation. The basic strength of the chelating group, the stability of the chelate complexes formed by a given metal ion generally increase with increasing basic strength of the chelating agent as measured by the pKa values. The nature of the donor atom in the chelating agent, ligands which contain donor atom of the soft base type from their most stable complexes with the relatively small group of class B metal ion and are thus more selective reagents. This is illustrated by the reagents diphenyl thiocarbazone used for the solvent extraction of metal ions such as palladium, silver, hydrogen, copper, bismuth, plumbum, zinc. Ring size 5 or 6 membered conjugated chelate rings are more stable since these have minimum strain. The functional group of the ligand must be so situated that they permit the formation of a stable ring. Resonance and steric effects. The stability of chelate structure is enhanced by contribution of resonance structures of the chelate ring. Thus, copper acetyl acetonate has greater stability than the copper chelate of a aldoxime. A good example of steric hindrance is given by 2,9-dimethyl phenanthroline, which does not form a complex with iron, as does the unsubstituted phenanthroline. This hindrance is that a minimum in the tetrahedral grouping of the reagent molecules. About a univalent tetra-coordinated ion, such as that of copper 1, a nearly specific reagent for copper is thus available. The choice of a satisfactory chelating agent for a particular separation should, of course, that all above factors into account. The critical influence of pH of the solvent extraction of metal chelate is discussed in the following section. Quantitative treatment of solvent extraction equilibria. The solvent extraction of a neutral metal chelate complex formed from a chelating agent HR according to the equation MnN positive plus Nr negative equilibrium MRN may be treated quantitatively on the basis of the following assumptions. The reagent and the metal complex exist as simple unassociated molecules in both phases. B. Solvation plays no significant part in the extraction process. And the solutes are uncharged molecules and their concentrations are generally so low that the behavior of their solution departs little from ideally. The dissociation of the chelating agent HR in the aqueous phase is represented by the equation HR equilibrium H positive plus R negative. The various equilibria involved in the solvation extraction process are expressed in terms of the following thermodynamic constants. Dissociation constant of complex Kc is equal to Mn positive W R negative Nw upon M R Nw. Dissociation constant of reagent Kr H positive R negative upon HRW. Partition coefficient of complex Pc is equal to MRNW mRNO. Partition coefficient of reagent PR HRW upon HR naught, where the subscript C and R refers to complex and reagent W and O to aqueous and the organic phase respectively. The distribution ratio, that is the ratio of the amount of metal extracted as complex into organic phase to that remaining in all forms, the aqueous phase is given by D is equal to MnRnO upon MrNW plus Mn positive W, which can be shown to reduce to D is equal to H power NO upon me H positive NW, where K is equal to PR whole the power N upon Kc and Pc. If the reagent concentration remains visually constant, D is equal to K star H positive N upon W, where K star is equal to K HR N upon 0. And the percentage of solute extracted E is given by L log E minus log 100 minus E is equal to log D is equal to log K star plus NPH. The distribution of the metal ion in a given system of the above type is a function of the pH alone. The equation represents a family of sigmoid curves when E is plotted against pH with the concentration with the position of each along the pH axis depending only some theoretical extraction curves for divalent metals showing how the position of the curve depends upon the magnitude of K star are depicted. Illustrates 6.2 figure how the slope depends upon N. It is evident that a tenfold change in reagent concentration is exactly offset by a tenfold change in hydrogen ion concentration, that is by change of single unit of pH. Such a change of pH is much easier to effect in a practice if pH 1 by 2 is defined as the pH value of 50% extraction. We see from the above equation that pH is 1 by 2 is equal to minus 1 by n log K star. The difference between pH 1 by 2 values of two metal ion in a specific system is measure of the age of separation of the two ion if the pH 1 by 2 values are sufficiently. The excellent separation can be achieved by controlling the pH of extraction. It is often helpful to plot the extraction curves of metal chelates. It one takes as the criteria of a successful single stage separation of two metals. By pH control, a 99% extraction of one with a maximum of 1% extraction of the other. For bivalent metals or a difference of 2 pH units would be necessary between the two pH 1 by 2 values. The difference is less for tetravalent metals. Some figures for the extraction of metal dithiogenates in chloroform are given in the table 6.1. If the pH is controlled by the buffer solution, then those metals with pH 1 by 2 values in this region together with all metals having smaller pH 1 by 2 values will be extracted. The pH 1 by 2 values may be altered of the extraction thus increased by the use of competitive complexing agent or of masking agent. Thus in the separation of mercury and copper by extraction with dithiogen in carbon tetrachloride at pH 2, the addition of EDTA forms a water soluble complex which completely masks the copper but does not affect the mercury extraction. Cyanides raise the pH 1 by 2 values of mercury, copper, zinc and cadmium in dithiogen extraction with carbon tetrachloride. That's all about this solvent extraction. Thank you so much.